Hello and welcome. In this video I'll be covering section 3.4, which is over optimization problems. My goal for you by the end of the video is to be able to solve real-life optimization problems. So we'll start with some guidelines on how we approach these types of problems. So essentially what we'll be presented with, more than likely it'll be some form of a word problem to then give us an idea of what the situation is. So we would first want to, of course, read the problem and then identify everything that was given to us, as well as everything that I need to determine or solve for. So another strategy that's usually pretty good with these types of problems is to actually sketch a picture if you have the ability to, I guess, provide yourself with a visual. After that, we want to write what our primary equation is. Basically, what that means is whatever I'm trying to either maximize or minimize, I need to determine whatever that primary equation is. So that could be anything from area to surface area to volume to just a sum or a product. So there's a lot of different possible equations that we can use for that. So we have to kind of do a little bit of research or rely on our memory for some of those particular types of formulas or equations. After that, we want to try and reduce that equation down to having only one single independent variable. So essentially, if I had multiple variables on one side of the equation, I want to try and substitute potentially what would be a secondary equation or an equation that relates the independent variables of the original equation that we're trying to maximize or minimize. We would basically use that equation, isolate one of the variables, and then substitute it in to the primary equation, so I will only have one variable left that would be independent on one side of the equation. After that, we want to just think of what types of answers make sense. So that would essentially be, as this fourth step says, to determine the feasible domain. So essentially, a lot of scenarios, if you think about just a real-world context, having negative answers come back oftentimes don't make a lot of sense in the real world sense. So essentially we just want to, I guess, determine what possible answers actually could happen. And if I end up getting answers that don't fall inside that domain, I just would not include them with my answer. And then the very end now, once we have everything kind of determined and set up for us, then we just fall back to the techniques that we've explored in the prior three sections. Where I could use the first derivative test or the second derivative test to essentially just determine whether I have a maximum or a minimum. So we could just utilize increasing and decreasing and that concept and just determine wherever that switch is. I know I would have either a high point on the graph or a low point on the graph. So essentially that's what we're going to be trying to solve for, is any high point or low point of our primary equation's graph once I've turned it into just one single variable on one side. So hopefully after I work through, it looks like I have about 4 examples here, hopefully after I work through those examples, everything here will kind of start coming together and making sense. So without further ado, let's go ahead and talk about the first example. This one, notice it just says we're going to find the maximum volume. So our situation that we have is manufacturers wanting to design an open box, so that means there is no lid. And we would want to have it have a square base and then a surface area that has been given to be 108 square inches. So if we start sketching a picture here, we've just got a box that would be open on top. And so if we said that the base of this is a square, I could then just define variables and just say that's an x by x on the bottom then. So again, this right here would be an open top. But I essentially just define some variables or come up with some variables that I want to use. I'm just going to go ahead and use x's and y's just because why not? But you could do l's and w's or h's for this. Since we have volume of a box, that's going to be an equation that I would want to, I guess, set up. So in this case, my volume equation for this box would be x times y, so length times width times height, which really I could simplify and just say that would be x squared times y as our simplified version of that. And then it does give us a surface area. So if we think in terms of surface area, surface area for a box is going to end up being, if we think about kind of numbering our sides here, if I said that the front was 1 and the back was 2, those both have the same dimensions of x times y, so I know I have 2x times y. Then I have the right side, if I call that 3, and the left side, if I call that side 4. Those both have a dimension of x by y as well, so there's 2 more of those. And then there's the very, very bottom dimension, which is an area that's x times x. So if I simplify all of that, it looks like 2xy plus 2xy. I really could have said that's 4xy. And then x times x, that would be x squared. So 4xy plus a single x squared would be my surface area. However, with this one, it actually gave us what that value is, so that's going to be my secondary equation. This one right here, the volume, is my primary because that's what I'm trying to maximize. So my primary is the volume, my secondary is the surface area. Reason being is I can actually say, instead of calling it surface area equaling that, I actually know that value, which is 108. Because again, it gave me 108 square inches was my surface area. So what I'll want to do is try and use this secondary equation. So I'm going to focus my attention on this secondary first and actually try and isolate a letter. So it looks like to me there's only a single y, so I should be able to isolate that relatively easy. So I would do, if I off to the side just set this up, I've got 108 equals that 4xy plus x squared. I'd first want to subtract the x squared. So that would then give me 108 minus x squared is equal to 4xy. And again, I'm trying to get the y by itself, so I'll just divide by both 4 and x. And that then gives me an expression that I could say y is equivalent to this 108 minus x squared all over 4x. And if I could reduce it, I would, but it doesn't look like there's anything in common on top and bottom that I could factor and reduce. So that's really as good as that's going to get. So now I'll go to my primary equation, the volume equaling x squared times y. But essentially what I'm going to do is take this expression that I found y was equal to, and I'm just going to plug it in place of the y. So now my new expression is going to be my volume is equal to x squared times the 108 minus x squared over 4x. And now I'm going to actually look to see if I can simplify, because it looks like I've got x squared multiplying the top, but I do have this x on the bottom, so I really could say that this x that's on the bottom will cancel with one of the x's out front, and then just distribute that through and go ahead and rewrite it in a way that makes it a little bit easier. So I'm going to write this division by 4 really as a 1/4 out front. That way I can just treat it like it's a coefficient, and then in this case I would have x times 108 minus x times x squared, and then that's now what I'm going to need to figure out what the derivative is. So if I go ahead and find what v prime is now, v prime is going to be, I'll leave that 1/4 coefficient out front, 108x, its derivative would just be 108 minus, and then x cubed, its derivative would turn into 3x squared. So at this point I would think back to what do I need to do to come up with my critical numbers. So that would be essentially just whenever this equals 0. So if I set that equal to 0, really all I have to worry about is when is 108 minus 3x squared equal to 0. So if I added 3x squared, that would move it over to the other side, make it a little easier to isolate. That 1/4 that was in front really is not going to be a part of setting this equal to 0. So if you wanted to picture it like we technically multiplied both sides by 4 to cancel that 1/4, you could think of it that way, but 0 times 4 would stay 0. Then again, all I did was add the 3x squared over. At this point I should be able to just divide 3. And so if I go ahead and do 108 divided by 3, that turns into a 36 equaling x squared. And at this point now I should be able to take a square root and get that my critical numbers are going to be plus or minus 6. Now in the context here, this is where the feasible domain comes in. I do know that since this is a physical shape, my feasible domain is really x just has to be greater than 0. So that's going to actually rule out that -6 that I just got there. So really I only need to figure out what happens on each side of 6. Does it increase and then switch to decreasing, or vice versa? So I'm going to go ahead and just pick some numbers and test it here inside my derivative. So I'm going to plug into this part right here and just see if I get positive answers or negative answers. So if I choose a number that's less than 6, say like 0, plug in 0, I get positive 108. So that would be a increasing interval. If I plug in a number greater than 6, say like 10, 10 squared would be 100. 3 times 100 would be 300. 108 take away 300 would definitely go negative. So if we think in terms of, okay, it was increasing and then switched to decreasing, that means this must be a relative max at that value of 6. So what dimensions will produce a box with this maximum volume? I've just established that the x value is 6. So my dimensions, if I could actually find some room here, I'll just write it up in the top right corner here. My dimensions would be, this is in terms of inches, so it would be 6 inches by 6 inches by, and now I just need to plug 6 into my y expression right here off to the left. So I would just need to figure out what is 108 minus 6 squared, so that would be 36, over 4 times 6, so that would be 24. And if I go ahead and simplify that, 108 take away 36 would be 72, and then divide that by 24 gives me a value of 3. So the third dimension of this would be by 3 inches to be able to maximize this volume in this scenario. So hopefully that kind of made sense, that we started with identifying our primary and our secondary equations. The secondary was the one that used the number that they provided for us, which that's where that 108 got involved. I really just used my picture to kind of come up with those expressions, and then I just tried to replace the y value with its equivalent expression from our secondary equation. So just isolated the y, plugged it in, found my derivative, set it equal to 0, solve for the critical numbers, and then I used the increasing and decreasing, so essentially the first derivative test, to determine whether I had a max value or a minimum value at that number 6. And again, I was able to get rid of -6 because the context of the problem, I can't really have a negative side length. So as you can see from the first example, some of these problems can be pretty intense and there's a lot of things going on. But again, the general concept is we're just trying to come up with an expression that has a single variable on each side, find its derivative, set it equal to 0, and then use our first derivative, or we could even use a second derivative test if you really wanted to. But we just determine what the extrema is, and we just look to see what part of that, or out of the extrema, which one I actually want for that particular problem. So that last one was an example of maximizing. This one, as you can see, now is going to be I want to minimize. You'll notice that regardless of whether it says maximize or minimize, it really is not going to change our approach a whole lot. So anyway, let's go ahead and start this one. It says that the product of two positive numbers is 72, so I'm going to go ahead and just define a couple of variables for those two numbers. I'll use x and y, so x times y, it says, is 72. Since that one gave me a number that I could actually set equal to, that must mean it is the secondary equation. So that will be the one that I'm going to pick one of those variables to solve for or isolate, so I can substitute into my primary. So now let's go ahead and set up our primary. It says that we have the sum, so I'll just call that s, is equal to the second number plus twice the first number. So I'm going to go ahead and just write that where it's twice the first number, 2x, plus the second number, y, and that will be essentially, because that's what I'm trying to minimize, that must be my primary equation. So what I'll want to do is take the secondary equation and pick a letter to isolate. Looks like to me in my primary equation it will be easier to isolate the y. So I'm going to go ahead, or not isolate, but plug in for y, so I don't have to worry about the multiplying by 2 step. So if I just divide both sides by x, that will give me my expression for y, which is 72 divided by x. And then I'll go ahead and now plug that into my primary expression. So my s is equal to 2x plus, and then what y was just solved for, which is 72 over x, which I could really call that 72 times x to the negative 1, which is going to be helpful for the next step, which is find the derivative. So my s prime, in this case, is going to equal just 2 minus, in this case, negative 1 would multiply with 72 because this really has x to the negative 1 power. So negative 1 would come out, multiply with 72, make it negative 72. And then drop the power by 1, so negative 1 take away 1 would turn into a negative 2. And so now if I wanted to actually rewrite that or simplify it, get rid of that negative exponent, I could say that this really is 2 minus, and then 72 over x squared. And then that's essentially what I'm going to want to set equal to 0. So for this one, I probably want to get a common denominator. That way I can make it just a single fraction equaling 0, so I'd have to multiply top and bottom by x squared. That gives me a new expression of 2x squared minus 72 over x squared being equal to 0. Now is when we'd want to try and take into account what is my feasible domain. So it does say that I have to have 2 positive numbers. So off to the side, I know that x just has to be greater than 0 at that point. So if we look at what the critical numbers would be from this, the critical numbers would be whenever the top equals 0 and whenever the bottom equals 0. Setting the bottom equal to 0 is pretty straightforward. That would just be at 0 itself. But again, I know that won't be a possible solution because it has to be a positive number. 0 is not positive, it's in between. The next part would be actually solving when is the numerator equal to 0. So if I just said 2x squared minus 72 equals 0, I could add 72 over to the other side, and I get 2x squared equals 72. Divide that by 2, I'd get x squared equals 36. And take the square root, I would get x equals positive or negative 6. But again, it also needed to be a positive number or off to our feasible domain. I know it has to be greater than 0. So really it's just positive 6 that's my possible number to test. So I'm going to go ahead and just kind of throw all of the numbers on the number line just so it looks like what we were doing back in 3.1 and 3.2 for the increasing and decreasing. But really I only have to focus my attention on what's happening to the left and to the right of 6. So if I choose a number like maybe 3 and then another number maybe like 10, I'm just going to plug into my derivative expression. So into this right here is probably the easiest version. Squaring the number on the bottom is going to make the denominator positive no matter what I do. So I really don't have to worry about what's happening there. It's really just what happens in the numerator. So if I plug in, say, 3 squared would be 9, times 2 would be 18, but take away 72, that would definitely come back negative. Whereas if I plug in a number like 10 squared would be 100, doubled would be 200, take away 72, that would come back positive. So since that switched from decreasing to increasing, I then can make the conclusion that at 6, that would be a relative min. And since we were solving for x, I know that the first number in this case must be the 6. So x would equal 6. Y would equal 72 divided by 6. So just plugging into this expression right here, 72 divided by 6 would give me that y must be equivalent to 12. So those would be my two numbers that have a product that is 72, but then has a minimum sum if I was doubling the first number and adding it with the second number. Let's go ahead and try another example here. So this one, it wants us to find any points or all of the points that are closest to this point 0, 3, but they lie on the graph of y equals 4 minus x squared. So this is one that we could give ourselves a little visual for. 4 minus x squared would be a parabola that shifted up 4 places and then has an x-intercept or x-intercepts of positive and negative 2. So it would essentially be a parabola that opens down like so. And then the point 0, 3 would be this point that's directly below that vertex. So we're just trying to figure out what points that lie on the graph are closest to it. So it might be a couple of points that are just a little bit to the left and to the right. That might be a little closer than the actual vertex is to that point. But we'll let the math kind of determine whether that point really is, or those 2 points actually are the ones that are closest. So since we're doing a distance here away from a point, I'll probably need to utilize the distance equation, which in this case, if you remember the distance formula, was the square root of x2 minus x1 squared added with y2 minus y1 squared. And so I really just need to figure out, how do I write these points in that x comma y format? Well, the first one, the 0, 3, that's pretty easy because they gave me that one. The second one would just be some arbitrary x paired with a y, but it's telling us that y is this 4 minus x squared. So I can actually kind of substitute that in place of the y. And then now I should be able to plug those points into the distance equation over here and see if maybe it can simplify a little bit. So if I subtract the two x's, I'd have x take away 0, quantity squared, added with, and then the y's would be 4 minus x squared, take away the 3, quantity squared. So if I simplify that, looks like I should be able to say x minus 0 is just x, squared would be x squared, added with, and then here if I go ahead and combine 4 take away 3, that really would just be 1 minus x squared, quantity squared. So I'll probably want to expand that out because there will be a like term that can combine with the x squared. So I've got x squared plus, if I did expand this, I'd get 1 minus x squared, so that's really minus 2x squared in the middle, and then plus x to the 4th. So the thing I'm going to take the derivative of, I'm going to go ahead and rewrite this in descending order, so it would be x to the 4th. I have x squared take away 2x squared, so that would really be a negative x squared in the middle, and then plus 1. So that is in quadratic form. So if I needed to find the zeros of that expression, I technically will be able to, utilizing the quadratic formula more than likely. It looks to me like that probably is going to only have imaginary solutions, but we can try that out in the event that we actually need to deal with that. So now we're on to the, let's find the derivative step. So with this one, the derivative of that expression, I can picture that square root as a 1/2 power, so that according to chain rule, I'd have 1/2 come out front. The base of x to the 4th minus x squared plus 1 would stay the same. Power would drop by 1, so it now has a negative 1/2 power. But then I have to multiply by the derivative of the inside, which in this case would be 4x cubed. And then it looks like minus 2x. And then the plus 1 would just be 0, so I can close that off. So it appears that this 1/2 that's in front, I could distribute through that parenthesis and simplify it a little bit. So I'm going to go ahead and move this up into this blank area. My derivative is equal to, looks like I've got, if I distribute that 1/2 through, that would turn that parenthesis into 2x cubed minus single x, because I can divide both of those numbers by 2, and then the denominator would just be that square root of x to the 4th minus x squared plus 1. So my critical numbers are again going to come from whatever makes the numerator or denominator equal 0. So if I set 2x cubed minus x equal to 0, I should be able to factor in x out and get 2x squared minus 1 equals 0. So I know that one critical number is going to be 0 itself. And then the other one would be if I added 1 divided by 2 and then took the square root. So I'm going to go ahead and do that off to the side. I'd end up with adding 1 would give me 2x squared equals 1. Divide by 2, I'd get x squared equals 1/2. Which then if I take the square root, I get x would equal plus or minus the square root of 1/2. So that would be the square root of 1, which is 1, over the square root of 2, which is not able to be simplified, but I can rationalize. So this really would be plus or minus the square root of 2 over 2. So there's two more critical numbers to test out. Now I need to figure out when does the denominator equal 0. Well, that would be when the quadratic form on the inside equals 0. So let's just try quadratic form and see if it comes back as a real solution. So that would be the negative b, so negative negative 1 would be positive 1, plus or minus the square root of b squared, so that would be 1, take away 4 times the a times the c, all over 2 times a, so 2 times 1. 1 take away 4 is going to come back imaginary, because that would be negative 3, and the square root of negative 3 is an imaginary number, so I really don't have to worry about any more critical numbers. So that at least was somewhat nice. A lot of ugly numbers up on the screen though. So anyway, now I can go ahead and test these intervals by just putting my critical numbers on this line. So the square root of 2 over 2 is about 1.4, if I remember right. Let's double check it. Actually, no, that's the 0.7. So square root of 2 divided by 2 is, in fact, the value of 0.707. So if I chose something like negative 1/2, that should be safe in between here. So negative 1/2 and positive 1/2 are going to be the two numbers I'll test there. And then something less than and greater than each of those, that should be a little easier to come up with. Something like negative 5 and maybe positive 5, that would be pretty safe. So again, I'd be plugging into this expression right here. We've established that the denominator never would equal 0. So that technically is always going to come back positive no matter what number I plug in. So that part at least is somewhat nice. All I need to do is figure out what happens in the numerator. So if I plugged in a number like negative 5 cubed would be a negative 125, doubled would be negative 250, and then take away negative 5, that would really be just adding 5. That seems like that would still for sure stay negative. So that part of this is decreasing. If I plug in a number like negative 1/2 cubed would be negative 1/8. 2 times negative 1/8 would turn into negative 1/4, but then minus a negative 1/2 would really switch to plus 1/2. Negative 1/4 plus 1/2 would go positive, and the denominator is always positive, so I know that must be an increasing. If I do a similar step here with 1/2 cubed would be 1/8. 2 times 1/8 would be that 1/4. Subtract 1/2, that would come back negative 1/4, so that's a decreasing interval. And then a number like positive 5, if I plug that in, 5 cubed is fairly large, doubled, pretty much going to come back positive here anyway, but that would turn into 250, take away 5, that would be 245, positive. And again, the denominator we already established was always positive. So anyway, what does that now give us? Well, I've got a decreasing to increasing happening here at negative square root 2 over 2, so that must be a relative minimum. At 0, it switched from increasing to decreasing, so that must be a relative maximum. I'm looking for the ones that are closest, so I really don't want that one. And then the rad 2 over 2, it's decreasing, switching to increasing, so that one's also a relative min. So this one, it appears, has 2 points that are the same distance away, which kind of makes sense according to our picture up to the right there. So what are those ordered pairs? Well, one of them is going to have negative rad 2 over 2 as the x value. The other one's going to have positive rad 2 over 2 as the x value. And to get the y value, all I have to do is just plug it in. So if I did 4 take away, it should be the same y value, because squaring each of these is going to come back positive. So it's really just going to be square root of 2 over 2 squared, which is 1/2, or 2/4, which reduces to 1/2. So 4 take away 1/2, that would be 3.5, which 3.5 really would just be 7/2 as a fraction, or you could write it as 3.5. But those would be my 2 points that would be closest to the graph, or that are on the graph that are closest to that point 0, 3. So a little bit intense with the numbers on this one, but again, hopefully the concept that we're trying to do here of set up the expression, find the derivative, set it equal to 0, and then test my intervals to see what kind of extrema I have. Hopefully that process that you've seen so far with the other two examples combined with this one, it's starting to kind of follow at least a pattern that you can remember when it comes to doing these types of problems. All right, let's go ahead and do one last example. This one is relatively close to one of the problems in your homework assignment, so this one might be potentially the most useful out of the examples here, at least when it comes to completing your assignment. So with this one, it's giving us that we have the combined perimeter of a circle and a square is 36 inches. So since that one was the one that they gave us a value for, this is more than likely our secondary expression. Let's go ahead and set that up. Remember, perimeter of a circle we actually have a special name for called circumference, which was 2 pi r. Then I would add it with the perimeter of a square. Well, if we just said a square had a side length of x, all of the sides would be the same, so that should be perimeter is 4x. Then that would equal the 36 that they said that the perimeters combined to equal. Now we need to set up our primary expression or equation, which in this case is a total area, and we want to minimize it, so we're looking for a relative minimum on this graph that we're going to create. So we've got, for this one, the area of a circle should be pi r squared, added with the area of the square. Well, if I gave the square a side length of x, the area of that would just be x squared. So out of those expressions, let's see, it doesn't really look like either one of those is going to be that much easier to, I guess, solve for. Maybe I'll go ahead and try and replace the x, so try and isolate x over with this expression here. So if I wanted to start trying to isolate x, I would subtract the 2 pi r first. That would then give me 4x is equal to 36 take away 2 pi r. And then I would just need to divide both sides by 4, which it looks like I can reduce that a little bit and say that x would be equivalent to, those are all divisible by 2. So I could say that that's really 18 minus pi times r over a 2. So that expression I'm going to replace the x value over here in our primary with. So it's pi r squared is just going to stay the same, but the x squared is going to get replaced with 18 minus pi r over 2, quantity squared. And so now it's the derivative step. So it is, I guess, important to note the domain of this one. I can't really have negative radius or a negative side length, so I do know that both r and x need to come back as positive values. So just important to kind of note that before we get any further. If I go ahead and find the derivative of this, it looks like I could go ahead and just take the power of 2 out front, so that would become 2 times pi times r. And the power would drop by 1, so it would just be r to the first power added with, and this one I can do kind of a chain rule situation, so 2 would come out front, 18 minus pi r over 2 would stay the same, the power would drop by 1, so that would technically have a power of 1 right there, which we don't need to write. And then multiply by the derivative of the inside, so if I kind of separated that, 18 divided by 2 really would be 9, minus pi over 2 multiplying with r. So if I just think in terms of what would the derivative of that be, well, 9 would turn into 0, and then negative pi halves times r, that would really just be negative pi halves, or the coefficient on the r. So at this point, let's see what we can do to maybe simplify this. Looks like I've got 2 divided by 2, so those two can at least reduce a little bit. And let's see, what else can I maybe do here? Looks like I've got a pi in both terms, so I could factor pi out. And that would leave me with 2r plus, and if I distribute the 1/2 through, or the negative 1/2 through here, that would just turn into a, let's go ahead and just switch that to a minus sign. So the negative that's right there, we'll just switch the plus to a minus. And now I've got 18 minus pi r, that would be over 2, which again I could split that up if it makes it easier to try and solve this, because really what the next step is going to be is I'm going to try and set this equal to 0. So if we did that, I could divide both sides by pi. That would cancel the pi that's in front. So that would give me 2r minus this 18 minus pi r over 2 being equal to 0. So to deal with that fraction, I could just distribute it 2 through on both sides. That still stays 0 on the right, but that'll make this 4r minus now 18, and then if I distribute that negative through, that would become plus pi times r, because again the 2 divided by the 2 would cancel out, so it just leaves the numerator, and distribute that negative that was in the middle, or the subtraction that was in the middle, through that. That gives me this expression. So it looks like I do have some like terms. I could say that the 18 could add over to the other side, and that would give me something where I could factor r out, which would be r times 4 plus pi being equal to that 18. So to solve for r, I would just divide by that parenthesis 4 plus pi, which in this case does not really simplify, so I know that the radius of my circle is going to be that value, 18 over 4 plus pi. I guess I really should be verifying that this is truly a minimum, so if I go ahead and just put that one critical number that I got on my number line here, I just need to test what's happening on the left and right. It did come back positive, so that's at least good. But if I were to plug that into my derivative expression, let's see, what would be the easiest one to plug into? Probably this one. Let's see, decimal equivalents. Let's go with 18 divided by that 4 plus pi. It's about 2.5-ish. So since that's like 2.52, if I chose a number like 0, that's for sure going to give me some value, and I choose a number like maybe positive 5, that would give me a different value to determine whether it's increasing or decreasing. So if I plug in 0, I get 0 minus 18 over 2, so that would be 0 take away 9, which is negative, so that must be decreasing on the left. And then on the other side, if I plug in like positive 5, I'd end up with 2 times 5 is 10, take away 18 minus 5 pi. So since pi is close to just a little bit more than 3, that would be like 18 minus approximately 15. So that would be close to 3, just a little bit less than that. Then divided by 2, that's going to be a pretty small number. And 10 take away a pretty small number is going to stay positive. So that would be an increasing interval. So that is truly a relative min, because it switched from decreasing to increasing. So that's going to give me at least, or my radius dimension. So I at least have the dimension of the circle. The radius of the circle is that value. I just need now to come up with the side length of the square. So that would be just plugging into this x expression right here. So that's going to be a little bit tricky to do. I'll do that off to the side. I've got 18 minus pi times that, which would be 18 over 4 plus pi. Then all of that divided by 2. So if I distribute the pi through, I'd end up with 18 minus 18 pi over 4 plus pi, and then all over 2. So I would need a common denominator here with that one, so I'd have to multiply by 4 plus pi. 4 plus pi, that will have to have 18 distribute through it. So I've got 18 times 4. Then I'm going to subtract, actually no, 18 times 4, that's just going to stay. So that would give me 72. Then I've got 18 times pi that will subtract with the 18 pi, so that would be actually gone. So it's going to be 72 over 4 plus pi, but still over the 2 that's on the bottom. These numbers are super fun, as you guys can see. So really I just have to divide that numerator in half, so that would turn into a 36 over 4 plus pi for my side length for the square. So to sum up the dimensions here, I've got my radius was the 18 over 4 plus pi, and now I've got my side length of the square is this 36 over 4 plus pi. Such normal numbers, of course. But those would be, again, the dimensions that technically would minimize the total area, but still have the perimeter that adds up to that 36 inches as it presented. So anyway, hopefully this video has been helpful. I realize it's a super long one, but I think you guys kind of see the explanation for why this one turned into a pretty long video. The examples do take a little bit more because there's a lot more going on. But as always, if you have questions, just reach out, let me know. I do appreciate you guys taking the time to watch this video, and we'll catch you next time.